In this video, we're going to talk about something called elementary matrices. And all these are matrices that come about by taking an identity matrix and performing one elementary row operation on that matrix. By way of a reminder, there are three elementary row operations. One says that we can change the order of two rows. Another says that we can scale a row by multiplying it by some constant. And then, of course, we'll replace the old row with the new scaled row. And then the third one says that we can take some multiple of one row and add it to another row and put that in place of the second of those two rows, usually. So those are the elementary row operations. And an elementary matrix is an identity matrix that has been modified by one of these operations. It's quite common to do examples in this course with a 3x3 matrix just because it's bigger than a 2x2, which is almost a trivial case, but not so big as to be unwieldy. So almost all of the examples that we do are going to be on 3x3 matrices. I'm going to do them on 4x4 matrices here, just because I want to make it clear that when we do these examples, we're not necessarily, we're restricting ourselves to 3x3 for ease and convenience, but it's not always the case that that's what you'll be working on. So I'm going to start with I sub 4, which is the identity matrix with 4 rows and 4 columns, 4 pivots, each of which is a 1, and it's in reduced echelon form. That's the identity matrix of dimension 4. And in each case, then, I'm going to show the elementary matrix that comes about from each of these operations. So to make my notation clear, I'm going to call this row operation 1, row operation 2, and row operation 3. And I'm going to create 3 new matrices. I'm going to call them E1, E2, and E3. So let me move that down a little bit. E1 is the matrix that we get when we perform elementary row operation 1, that is switching 2 rows, on the identity matrix I. In this case, what I'm going to do is I'm going to interchange rows 1 and 3. And that's going to give me row 1 down here and row 3 up here. And everything else stays the same. This is what I'm going to call elementary matrix 1. Elementary matrix 2, this is just for the identity matrix and with dimension 4, I sub 4, and I'm going to use specific constants here because this is an example rather than a generalization. So my E sub 2 is going to contain the results of some specific constant multiplication, but that's not always the number that we would use. I'm going to say for this case, my constant is, let's see, C equals, let's go with -3. That means that my elementary matrix 2, the one that I get by performing elementary row operation number 2 on the identity matrix of dimension 4, is what I will get by multiplying one row by -3 and putting that back into the position of the same row. And I'm going to choose row 2 this time for my example, partly because I want to make the point that I'm not stuck working with rows 1 and 3. I just chose those for my first example. All right, so I'm changing row 2 this time. So rows 1, 3, and 4 don't change, but row 2 is the same as it was, only multiplied by -3. So that's what I get when I multiply one row by a constant and replace that row with the new values, but based on starting with an identity matrix. Elementary matrix 3 is going to be what I get when I take one row, multiply it by a constant, add it to another row, and replace the second row with the result. And I'm going to use 2 for my constant this time, and I'm going to work with row 3 and 4. So I'll replace row 4 with my result. So what I need to do with each of the entries in row 3 is multiply it by 2. It's going to give me a 2 in this position. So I'll have 0, 0, 2, 0, and then I'm going to add that to row 4. So that's going to be 0, 0, 2, 1 in row 4. 0, 0, 2, 1. The other rows don't change. Oops. Getting ahead of myself there. This is elementary matrix 3, or E3. Now again, remember that these are specific constants. I'm adding 2 specific rows. In the generic case, first of all, I don't have to work with I4. I can work with any identity matrix. And I might have different constants. I very likely will have different constants. I may be multiplying and adding together 2 different rows. I may be reversing the order of 2 different rows besides just rows 1 and 3. But this is an example of what it means to create an elementary matrix. On the next slide, I'm going to show you why these elementary matrices, or how these elementary matrices can be used. Okay, so here are our elementary matrices again. Elementary matrix 1 is the one that we got by reversing the order of rows 1 and 3. This used to be row 1. This used to be row 3. Elementary matrix 2 is what we got when we multiplied row 2 by -3. That's the only operation we did on that matrix. And elementary matrix 3 is what we got when we took a multiple of row 3, namely 2, and added it to row 4. Okay, and then I've also put a matrix A up here. I've selected for the matrix A something with relatively small numbers, lots of zeros and a couple of negatives, just to make the point. One of the things I'm going to do first here is I'm going to do an operation on matrix A that's equivalent to doing that same operation on the elementary matrix, and we'll get a new result from that. And then I'm going to show you why, or a way in which these elementary matrices can be useful. So let me first do, let me call it, I kind of want to change where A is. That's better. Okay, so now I can, now I've got a little bit of room here. What I'm going to do next is I'm going to find what I would call A1, which is the matrix that you get by switching rows 1 and 3 in matrix A. Well, row 1 used to be 1, 2, 2, 1. Row 3 used to be 1, 2, 1, 1. And everything else stays the same. So my row 2 was 0, 0, 2, 3. That doesn't change. And my row 4 was -1, 2, 0, -2. That doesn't change. All right, that's how we've always done this in the past. But I'm going to do something a little bit different now. I'm going to do matrix multiplication involving E1 and A. That is to say that I'm going to take the elementary matrix that I obtained by reversing rows 1 and 3. And I'm going to multiply it by matrix A. This is why I chose lots of ones and zeros in my matrix A, especially since I'm using a 4x4 matrix. All right, I'm going to do this relatively quickly, but I'll point out that I'm setting the stage for myself by saying that this is a 4x4 matrix times a 4x4 matrix. So I can do this multiplication and the result will be a 4x4 matrix. So let me set up the matrix where I'm going to write my answer. Give myself lots of room. And I'm going to start with row 1 times column 1. And as you can see in the elementary matrix, there are lots of zeros. So anytime I have a 0 times an entry, I'm going to get a 0. And since I'm multiplying an entry times an entry and then adding that to the product of another entry and adding that to the product of another entry and so on, I'm basically only going to be getting a multiple of 0 except for where there's a 1. So in elementary matrix 1, I have in row 1, I have the third position is a 1. So I'm going to multiply that by the third position in column 1, and that's going to give me a 1. So I know from that my entry here is going to be 1. 0 times 1 is 0. 0 times 0 is 0. 0 times -1 is 0. It's only the 1 times 1 that gives me a non-zero number. When I add those all together, I get a bunch of zeros plus 1. Then I'll do the same thing again for column 2. I'm going to get a 0 plus a 0 plus something plus a 0 because the first, second, and fourth entries in the elementary matrix are in the first matrix here are zeros. So I get 1 times 2. And essentially you can see that what's happening is that in my first row, I'm getting a copy of matrix A's third row. 0 times everything except the third entry is going to give me 0 plus 1, 0 plus 2, zeros plus 1, zeros plus 1. Then I'm going to go to the second row in the elementary matrix and proceed the same way. But what's going to happen now is I'm going to get zeros times everything in this column, everything in this column, and so on, except for the second entry. And the second entry is the second row. So I'll get 0 times 1, 1 times, 0 times 1, 1 times 0, 0 times 1, and 0 times 1. So in this case, that's actually 0. The whole thing is 0. But as with the previous row, with this row, everything I get when I multiply each individual entry here by each individual entry in each column is going to be 0 except for the second term, right? So essentially what's going to happen here is that I'm going to get zeros except for the second entry in each one. So I'm going to get row 2 from matrix A. In row 3, the first entry is non-zero for the elementary matrix. Everything else is 0. So when I multiply these zeros by anything over here, I'm going to get 0. I'll add those zeros to what I get when I multiply 1 by the first column and then the second column. And so it's going to reproduce row 1. And row 4 in the elementary matrix is going to reproduce row 4 in matrix A, because that's where the 1 is. Everything else is a 0. Whoops, copying the wrong thing there. It should be -1, 2, 0, -2. And I'm calling this the elementary, the matrix you get by performing, let's put that in a different place. This representation is specified by the actual matrices E1 and A. The result of that multiplication is this new matrix, but notice that that new matrix is what we called A sub 1. It's the same thing. 1, 2, 1, 1 in the first row, 0, 0, 2, 3 in the second row, 1, 2, 2, 1, and -2, 0, -2 in the third and fourth rows. So one of the ways in which these elementary matrices can be useful is that left multiplication by an elementary matrix onto another matrix. These will all be square matrices, right? The elementary matrices anyway are square matrices. Elementary multiplication from the left produces the same thing as though you had just done that row switching directly. Well, row switching is pretty easy. So if I wanted to switch rows 1 and 3 in matrix A, I would just rewrite it. But that's with a relatively straightforward and a relatively small matrix, right? What if you had a 17 by 17 matrix, or what if you had a 4000 by 4000 matrix? Chances are the data from that, or the entries from that, would come from a spreadsheet or part of a computer program, and the computer would be doing this. But this is what the computer's doing in that case. It's multiplying two matrices. The nice thing about elementary matrices is that I can write an elementary matrix for any given dimension in one step, right? For example, what if I didn't want, what if I wanted to generalize E2? Then instead of a -3 here, I would just say some number A. And then that operation would be to multiply row 2 by the number A, and A could be any real number. So I'm going to put my -3 back in there just for now. Oops, let's do it in the right color. -3. Okay, I've moved my resulting matrix from doing the matrix multiplication version of this problem. I've moved that up here and reminded myself that it's equal to A sub 1, which is what I got when I did the operation directly. Reverse rows 3 and 1, reverse rows 1 and 3, and you get this matrix. And I'm calling that A sub 1. All right, and I've moved that now, moved the corresponding matrix. And the reason I've moved it is because I now want to do, I want to find A sub 2. And I'm going to do that directly first. I hope I have enough room here. Let's try that one more time. I'm going to try to write a little bit smaller so I can get this all onto one screen. A sub 2, if we take as the operation number 2 in this case to be multiply row 2 by -3, then A sub 2 should be 1, 2, 1. Nope, sorry, that's the wrong matrix. I'm copying from A1 instead of A itself. 1, 2, 2, 1, 0, 0, 2, 3. This is actually A. 1, 2, 1, 1, and -1, 2, 0, -2. But I don't, this is not the right row 2, because that's from matrix A, 0, 0, 2, 3, and A sub 2 is going to come around. If I do the operation directly on matrix A, it's going to be, what will I get if I multiply row 2 in matrix A by -3? And the answer is 0, 0, -6, -9. So that's my A2. And now I'm going to look at how, what the result would be if I did it using elementary matrices. So I'm going to take E sub 2 and multiply it from the left by matrix A. That will give me 1, 0, 0, 0, 0, -3, 0, 0. Lots of zeros in these matrices, and that's really the point of an elementary matrix. They're all zeros, except where in the identity matrix there would have been a 1, and in the case of E1, they're still all 1s and 0s, but where the 1s are is a little different because we've switched 2 rows. In elementary matrix 2, instead of a 1 in one of the 4 pivots, we have a different constant. And in elementary matrix 3, we have the combination of a multiple of one row plus another. So in elementary matrix 2, I have, in this case, remember this is a specific value of A that I chose, -3. I've multiplied the row 2 by -3. And now what I'm going to do is multiply that matrix by my original matrix A, which is 1, 2, 2, 1, 0, 0, 2, 3, 1, 2, 1, 1, and negative 1, 2, 0, negative 2. And I'll use the same argument here. First of all, it's a 4 by 4 matrix times a 4 by 4 matrix. So I can do the matrix multiplication, and that will result in a 4 by 4 matrix. And second of all, multiplying row 1 first by column 1 and then column 2 and so on is going to result in entries that are 1 times the entries in column 1, 1 times the first entry in column 1, plus 0 times everything else. So I'm literally just going to get the first entry in each column as my first row. The same thing will happen with rows 3 and 4. 0 times 1 plus 0 times 0 plus 1 times 1 plus 0 times 1. And let's just pick a different one. 0 times 2 plus 0 times 2 plus 1 times 1 plus 0 times 0. And so this row, multiplying all of matrix A by this row, is going to reproduce row 3. And the same thing will happen with row 4. The only difference here, let me write these down. I can't think and talk at the same time. The only difference in this case is in row 2 of my elementary matrix. Instead of a 1 here, I have a negative 3. But everywhere else, I still have a 0. So I'm going to get 0 times 1 plus negative 3 times 0 plus 0 times 0, 1 plus 0 times 1 for my first entry in row 3. And that's 0 because even the second entry here, when I multiplied it by the second entry in the column, I got a 0. And the same thing will happen in column 2. 0 times 0, 3 times 0, 0 times 2, 0 times 2. So that's also going to be 0. So if you imagine that this was a 1, then you could see that what I'm reproducing here is row 2 rather, sorry, this row right here. But instead of just reproducing it directly, I'm getting a copy of it as though it were multiplied by negative 3. 0 times 2 is 0. Negative 3 times 2 is negative 6. 0 times 1 is 0 times 0. So negative 6 is my entry. And lastly, 0, negative 9, 0, and 0. So my last entry there is negative 9. And normally I wouldn't do row 2 here last, right? I would just do them in order, but I did it last because I wanted to first reinforce the idea of a row with a single 1 in it and all other entries 0 are just going to reproduce the corresponding row in the other matrix. Left multiplication does that. But also this one was the one that was different. So I did the others to reinforce the idea of the zeros and the 1, and then use that idea to say, well, look, there's a bunch of zeros here too, except instead of multiplying the entries in a column by 0 and 1, in this case, I'm multiplying them by 0s and negative 3. So it produced a slightly different row 2. But it shouldn't come as much of a surprise because that is my A2. That's exactly what I got when I did that, when I performed the elementary row operation directly on the matrix A. I multiplied the second row of matrix A by negative 3, and I got this row right here, which is what I got when I did it using this left multiplication of an elementary matrix. I could do the same thing for elementary matrix 3, but I'm going to leave that to you as an exercise. Try multiplying row 3 by 2. Row in matrix A, multiply row 3 by 2, and then add, so I'm here, multiply row 3 by the number 2, and add that to row 4, and replace row 4 with the result. Once you've done that, try it this way. Take this elementary matrix and multiply it on the left by matrix A, and you should get the same result.